condition given by an equation. We're supposed to prove an inequality involving terms that are not in the equation. Now, dividing the initial condition or equation by x is motivated because x to the 8th divided by x is x to the 7th. Now, that really doesn't come to fruition too quickly right here, but if you'll notice what happens here, you kind of postpone things a little bit. You take the time to factor the numerator. Okay, you take the time to factor the numerator, and you don't actually divide through by x until the end, it turns out. At least that's the approach I took. Now, notice right here, all we really did is take advantage of the property that if you have AB divided by x, where A and B can just be any numbers or expressions, okay, AB divided by x is actually the very same thing as A over BX. And that's really, it's a simple idea, but sometimes you don't see simple ideas when you're working a problem that looks like this, or at least me. Okay, so A times B over X, right? And that simple property about fractions is what actually happened here. Notice that this part right here would be your B, right? Okay, and so you actually, when you take this piece right here and divide it by x, you get x plus 1 over x. And you're wondering why that's important. Well, that comes up here pretty quickly. Notice there's this, I took this piece right here, okay, that was a result of this fractional property. And there's something called the AMGM inequality. Let me write it down here. It says if you have two real numbers, probably two complex numbers also, and you divide them by 2, which is just the arithmetic mean, okay, divide by 2, okay, that's guaranteed to be greater than or equal to the square root of the product of the two things. Okay, so I'll put square root x times 1 over x. Okay, but notice this works out very nicely because this is just equal to 1, right? That's just equal to 1. And so you see how this comes out. In other words, the net effect of this is that x plus 1 over x. X plus 1 over x right here, and we multiply by 2 is greater than or equal to 2. So you see, that's this 2 right here, properties of equalities in this 2, that's where this 2 comes from right here, right? Okay? All right, now, but notice this object is still just equal to 17 over x, right? It's equal to 17 over x, so we get this statement by doing a substitution. In other words, we just physically substitute 17 over x since it's equal to all of this, right? All right, and we get this statement right here. And when you multiply everything, when you divide by 2 and multiply by x, and we're assuming that x is positive here. I probably should have said that at the beginning. Okay, when you multiply, when you divide by 2 and multiply by x, you get 17 over 2. Let me create some more space here. You get 17 over 2. Okay, 17 over 2 is greater than or equal to, now remember, we're multiplying by positive x here, so that would be x to the 7th plus x. And let's see, that was what we were trying to prove, right? We're supposed to prove that x to the 7th plus x is less than or equal to 17 halves, and that's what we've done right here. X to the 7th, sorry I don't have it all on the same screen, but x to the 7th, we're trying to prove that x to the 7th plus x is less than or equal to 17 halves, and that's what we've done right here, okay? So we can do QED. And I find this kind of problem fascinating because we have no idea what x is, but if it's a solution, a real valued solution, positive real valued solution to the given equation, then this condition has to hold. And so let me just write that. I should have written that down at the very beginning. We presume, and I didn't really remember that until I went through the proof of it, but x is a real number greater than, I guess, greater than or equal to 0. Okay. And it certainly holds just trivially if x is equal to 0. So any x greater than or equal to 0, if it's a solution to the given equation, you get this result. And that's all.